There we go. So this is from last week's lecture. We were talking about the regular expression, how we describe the scientific notation in base 10. It's not perfect, because it still allows a non-normalized scientific notation, because the first digit can still be a 0, which means it is not normalized. The first digit has to be between 1 and 9 in order for the mantissa to be normalized in base 10. But we're going to overlook that little minor issue here. Okay? All right, so you guys will have a project to not only to parse, but also to convert a base 10 scientific notation and store that internally as a double. Okay, now when I say double, once again, it's basically the abbreviation of the IEEE double precision floating point number representation, which is kind of the topic that we have been on for about a week or so. Okay, so are there any questions regarding the scientific notation itself, base 10 or otherwise? Okay, so no question about that. And I believe this class is a little bit behind the Tuesday, Thursday class because we lost a Monday. Okay, so this is our chance to catch up. So on the Tuesday, Thursday class, I actually spent the entire class to write a parser for a base 10 scientific notation. So what I'm going to do in this class is just to give you the source code, which I gave to the other class as well, so that you guys can at least study that. There's nothing special about that parser other than a few things which I will point out in today's lecture. And then we'll move forward to talk about how do we convert from a base 10 floating point number representation or scientific notation, basically they mean the same thing, to a binary representation. So that will be the focus of today's lecture. All right, so I'm going to stop the YouTube, okay, because there's no need to replay that. And we'll focus on the scientific notation. And I got the source code already done. In fact, the debug session is still active from last time. So let me show you the source code. All right, so I'm not going to show the program in a sequential manner. You guys can read it if you want to in a sequential manner. This is the main program. And as you probably already know, the main program is the entry point of any C and C++ program. And this one is no different, except you can see main itself takes on 2 arguments in this case. Okay? In your previous classes, unless your professor in cisp310 kind of really spends the time to talk about the arguments being passed to main, this is probably new to most of you. So I'm going to explain that part. ARGC stands for argument count, and ARGV stands for argument value. These are the arguments being passed to the command line interface itself. In other words, if you are to run a program on the command line, you can type the name of the executable and then followed by any number of things that you want to specify. Those are called arguments. So this is the way a program written in C can gain access to those arguments. So instead of using standard in to input the number to be converted, you can now specify as a part of the argument. Okay? ARGC is at least 1 because the path of the executable is always ARGV0. ARGV itself can be seen as an array of pointers to const chars. In other words, it is an array of strings. The first string is always the path of the executable. The second string is going to be the first actual argument that you specify after the name of the executable. Is that okay? When I run the program, it'll be obvious what that's actually doing. So when ARGC is greater than 1, I got stuff to do. When ARGC is less than or equal to 1, which means it's exactly 1 because it cannot be less than 1, I basically just complain and say, not enough arguments because I'm expecting a base 10 scientific notation to process. Is that okay? Now, result is a local variable. It is initialized to 1. And it's going to be returned here. This is a convention also used by at least Linux and Unix. When an executable returns a code of 0, it means everything was okay. Execution terminated normally. Any value other than 0 means, nope, we had a problem, okay? So which value you want to return for what problem, it kind of depends on the program itself. So in this particular case, I just use a non-zero to indicate we have a problem, and if it returns a 0, it means everything was okay. So what if argc is greater than 1? Well, then I call the subroutine called parse with argv1, which is the second argument, which is basically the actual argument, the number to be converted. And I also pass the address of PD. PD is a structure of the type parseddata, which was defined like really, really early on. If you're not used to a struct, blah, blah, in C, it's basically the same thing as using a class to make an object. But the syntax is slightly different because in C++, you do not say class and then the name of the class and then the variable you want to declare. You just use the class name. In C, you have to use the word struct in order to have the compiler to understand we are trying to make an object of this particular struct type. Otherwise, it's basically the same thing as a class where everything is public. So are we okay so far? All right. So the next thing we want to do is to take a look at parseData itself and also the subroutine called parse. Are there any other questions about main before we go back earlier to take a look at those definitions? No questions. All right. So let's go ahead and go back to the very beginning of the entire program. Okay, so here's parseData. So parseData is basically looking at a scientific notation in base 10, and it tries to remember the sign. Sign being 0 means it is non-negative. Sign being non-zero means it is negative. Is that okay? All right. exp10 stands for the exponent in base 10, which is basically, it's kind of like the number that you specify after the lowercase e when you specify a scientific notation, but it's not quite the same. I'll explain that later. Now, the mantissa, okay, exponent 10 is a signed number in base 16 because we can't really specify a range in base 10 that is too wide, okay? So a 16-bit number signed is enough to contain that entire range. Now, mantissa is the funny one because when you specify the mantissa, especially because I try to make sure it is normalized, you would think it's going to be a float itself. But that would be kind of self-defeating because I was writing this program to convert from base 10 scientific notation to a double. If I use the double here, that's just kind of like, it's a chicken and egg problem, okay? So I can't use any actual double in this entire program. So mantissa is actually a 64-bit unsigned integer, which is a pretty big, pretty wide number. So how can I do this? Let's say we want to represent 1.23, okay? So if I want to represent 1.23, but I have the restriction of the mantissa can only be an unsigned integer, and the exponent can be plus or minus, any type of integer, how am I going to do it? What about making the mantissa 123 and the exponent of 10, -2? Would that have the same value? 123 times 10 to the power of -2, is that the same thing as 1.23? So that's how this representation is going to work, okay? All right, so now we look at parse, which is the actual logic of parsing. And the way I'm going to do this is I will leave the syntax description or the regular expression up there, so that way we can refer to the regular expression as I explain the logic in code. The first part I have to parse is plus minus with a backslash equal to. That means the sign of the number itself is optional. It may be there, it may not be there. If it's not there, the implicit sign is positive. So the way I do it is over here. Let me turn on line numbers in the editor so this way I can refer to the range of line numbers. So when you look at line 17 all the way to line 28, okay, that's processing the optional sign for the entire number itself. So how is it done? Side note is scientific notation, short for scientific notation. So that's basically the string that is containing the text representation of a base 10 scientific notation. So what I do is I dereference the pointer, which means I'm looking at the very, very first character, and I use a switch statement to find out what it is. If it's a negative symbol, then I increment side note to basically say, yep, I just processed one character, move on to the next one. I'm ready to process the next one. And then the sign is initialized to 1. Now, the sign is a member of the structure pointed to by PPD. Sorry. Okay, so it's a structure pointed to by PPD and is a member of that. This is basically the same thing as PPD and then the arrow to sign. Those two notations are exactly the same in terms of what they mean. This one does emphasize that PPD itself is a pointer. What it references to is a structure, and then with that structure, I want to access the member called sign. Okay. And then there's a break statement here, which means I'm out of the switch statement at this point. This is the only time that I would actually use a break statement because otherwise there's no easy way to get out of a switch statement. The second one is a plus symbol. If I see the plus symbol, I will also say, okay, I recognize this symbol. It can be a part of a scientific notation at this point. So I increment the pointer, so I'll be ready to process the next character. But then it falls through because there's no switch here. So it falls through, and what I do here is to initialize the sign of the structure pointed to by PPD to a 0, which means the number that I'm encountering is non-negative. Is that okay? All right. So line 17 all the way to line 28 is processing the optional sign of the scientific notation. Okay, what do we do next? Line 29 is just an initialization because all structures are uninitialized. Unlike in C and C++, there's no constructor. In other words, if I don't do this initialization on line 29, then the exponent in base 10 is some random number. I don't know exactly what it is. It's just whatever thing was occupying that piece of memory in the computer at that time. Okay, so line 30 is officially corresponding to the first digit of the mantissa. In other words, this digit here, okay, this guy here, is being processed by the condition of the if statement on line 30. IsDigit is a string function that is already supplied by the C library, so I don't have to write it myself. All it does is to check whether the character that I pass to it as an argument is between inclusively the ASCII code of 0 and the ASCII code of 9, which is what I'm looking for. Is that okay? If it is, I got some stuff to do. If not, there's an error condition because that digit is mandatory. It is not optional. I must have that digit. So if that digit is missing, I stop processing and go like, okay, no good. If it is there, then I do this initialization, and then I increment the string pointed by 1, or the character pointed by 1 to be more precise. Okay, what is line 33 doing? What is the right-hand side of the assignment doing? Go ahead. It's converting the ASCII code to the value of the digit of that ASCII. Okay, that's basically what it is. Because the character 0, okay, has an ASCII code of 48 in decimal. In other words, if I just use side note itself, it's going to give me 48, which is not the value that I want. What I want is the actual value of 0. So if I subtract the ASCII code of 0 from the ASCII code of whatever digit we know at this point is from 0 to 9, then I get the actual value of the digit itself. And then I put it into the mantissa because this is the first character that I encounter. I'll just stuff it into the mantissa for now. Okay? So what comes next? What comes next is the optional part of the fractional part of the mantissa. Okay? That part is optional. But how do I know whether that optional part is there or not? What do you think? What is the indicator? What can I use to look ahead a little bit and say, oh, I see there's the optional fractional part of the mantissa, or oops, there's no fractional part of the mantissa. What can I rely on? The dot, right? The decimal point. Yep. So that's exactly why there's this check of the decimal point. If the decimal point is there, okay, right after the digit, then I got some processing to do. So from line 30, well, I would say technically from line 36 all the way to line 44, is processing the optional part of the fractional part of the mantissa. Okay? So we'll look into that a little bit. Once I recognize the period, the dot, I skip over that because the dot, other than an indicator that we have a fractional part to the mantissa, really has no particular meaning otherwise. Okay, so once I recognize, yep, we have a fractional part, I just say, okay, now let's move on and process the rest. The rest is \d star, okay? \d star means any number of digits, including 0. So what I do here is I have a while loop, or a for loop. The for loop is basically saying, as long as I'm still seeing a digit, stay in the loop. Well, that kind of matches, the \d star thing, which is basically saying I can accept any number of digits. So as long as I'm still seeing a digit, stay in the loop. There's still stuff to process. This is the post operation. We'll explain that later. And what do I do when I see a digit? Two things. One thing, the first thing I do is to do this. I take whatever the mantissa was, multiply that by 10, which is basically left shifting it a little by one digit, and then I add the value of the digit that I'm currently seeing. So if I had 1 and I see a 2, that 1 becomes a 10, and then I add a 2 to it, it becomes 12. If I had 12 and I see a 3, then the 12 becomes a 120, and then the 3 is added to 120, so it becomes 123. So that's basically how we do a quote-unquote left shift, but in base 10. Okay? But because this is ignoring there's a dot here, that the digits I'm seeing here is on the right-hand side of the decimal point, and they represent negative powers of 10. So I need to subtract 1 from the exponent of the 10 exponent so that I remember, okay, in order to preserve the value that I'm seeing as the mantissa, we have to remember to subtract 1 from the exponent of 10. Is that part okay? So when I see 1, nothing is happening. When I see 1.2, okay, then the mantissa becomes 12, but then exponent of 10 becomes -1. When I see the 3, the mantissa becomes 123, but the exponent becomes -2. So that's basically how I track the mantissa, even though I do not use any floating point representation. If you want to summarize this technique, it's basically making the exponent explicit. I use a particular member in the structure to remember what kind of exponent of 10 I should be dealing with. Is that okay? All right. All right, so that part is optional. When this is done, okay, when I exit from this loop, what do I know for sure? What I'm seeing is not a digit. There are many things that are not digits, okay? So by the time I get out of this loop, which gets out of this conditional statement, then I end up on line 49. So on 49, I am processing the second optional part, which is this part here. It starts with an e, actual lowercase e, and then the plus or minus sign of the exponent plus the actual value of the exponent. But that part is optional too because of the \= So that means I'm only using the e to indicate, do we have an explicit exponent part? If the e is there, that means yes. Okay. If the e is not there, that means nope. Okay. The scientific notation does not actually have an exponent component. So if I do see an e, then I go through the rest of the logic, which basically starts on line 55. On line 55, I'm just skipping over the lowercase e itself, which is not a part of the value. It's nothing more than an indicator to say that, yep, we have an explicit exponent to this scientific notation. And then I use the same technique, basically, as earlier. I look at a digit, I look at a character that I'm looking at. If it's a negative symbol, I remember the exponent's sign is -1. Now this time it's not 0 versus 1 because later I use it for multiplication. If it's a plus, I remember it is the exponent sign is a 1 because once again I use it for multiplication purposes, and so it's useful to have it as -1 or 1. Is that okay? What if the sign is not there? What if, I just say E and then a 10, okay? Well, in that case, it goes to the default, which means do not skip over any characters because I haven't processed that digit yet. But at the same time, we can make the assumption that the exponent itself is non-negative. Okay? So now we move on to the for loop. So the for loop on line 68 is basically processing the digits that come after the E. So we'll handle that part first. And you can see it's about the same as the other loop, except I put a plus side note. Oh, the other one I did too. Okay, plus side note is a post operation, which means after each iteration, I add one to the pointer, so I'm ready to read the next character. And just like before, I stay in the loop as long as side note itself is pointing to a digit. The initialization has this kind of weird thing of O pointer equals to side note. In other words, I'm remembering what the character pointer is pointing to before I process any of the digits. So we'll figure out why I had to do that. The other one is kind of not too surprising. This exp is not exp10 as a member of the structure. This is just a local variable because I have to keep them separate. exp10 at this point may have a meaningful value already because of the way that I process 1.23. Okay, so it has a value of -2 already. I don't want to mess with that. Okay, so exp is by itself a separate local variable that I use to keep track of just the exponent itself in base 10. The logic of line 70 is something that's very similar to before, except I'm doing it to a local variable exp this time. So by the time I exit the loop on line 72, I know one thing. I'm not looking at a digit anymore, okay, because that's how I can get out of the loop. But at this point, I also want to know whether I saw a digit or not, because with a for loop, it's possible that I did not see a digit at all. So after the lowercase e, I see end of line or the null character to terminate the string right away. But that would not be syntactically correct because according to the scientific notation regular expression, \d is followed by a \plus, which means one or more occurrences of whatever is before. So I need to see at least one digit for the number to be legitimate. So that is when I use O pointer and compare that to side note. Because if I had seen at least one character, side note would have incremented. They would not be the same. The only reason why they would be the same after the loop is I did not see a single digit at all. Is that okay? So if I do not see a single digit, I say, okay, let's return a non-zero value to say that, oops, we got a problem. Okay, this number was not well formatted. Otherwise, I deal with the sign itself. So exp sign is a local variable remembering the sign of the exponent in base 10. exp is the exponent in base 10 that is explicit after the e. So I have to add that amount, okay, the sign times the actual magnitude to exp10, which is a member of the structure pointed to by ppd. Because only at this point do I know how much to adjust the exponent of 10 that is already in the structure. Is that okay? But at this point, I have seen everything that I can possibly see in a floating point number representation. So that's why I'm returning a 0, because everything is good. That's the only confirmation. And you don't see any returns until we get to line 91. So I'm basically playing by my own rules to not to use any return other than the end of a subroutine. I could have returned 0 here, return 2 here, return 1 here, and so on, but that would not be nice. That would make the logic difficult to track in the long run. In the short run, it's convenient, but in the long run, that makes it more difficult to track. So that's it. I mean, this is the parser code. It's known to work. I'll show you, how to check whether it works or not, and then we'll move on to talk about the conversion, so that we will be starting to catch up with the Tuesday, Thursday class. Is there anything in this program that you have not seen, language construct-wise, in cisp310? Maybe that struct thing, maybe, because they might be using class instead of struct. But other than that, anything, I mean, anything that you want me to explain any further in this program? If you understand most of it, it's just that the syntax of one or two little parts you feel kind of, I'm not really quite sure what that means. You can kind of look it up or ask me, in the lab or send me an email, okay? But I'm hoping that everybody understand the logic itself. It's not recursive. There's nothing really funky about this program other than main has arguments. But even that is fairly easy to understand, I would say. All right. So we'll go ahead and run the program just so that we know how it works. Okay. To run this program, you have to use a GDB, which is the GNU debugger, because otherwise the program actually does not produce any output. So there's no way to actually test the program. And I'm listing main itself, and since I already know the program does work correctly, I'm putting a breakpoint on line 109. And then when I run the program, this is the same thing as running it on the command line. So that means I have to give it something to process. Let's try 1.23, okay, because I kept using that as an example. So I give it 1.23, 1.23, press the enter key, it gets to result, and now I can print the local variable PD, which is a structure, and it tells me the sign is 0, which means the number itself is non-negative. Exponent in base 10 is -2, and the mantissa in base 10 is 123. But that's kind of what we talked about, okay? So let's go ahead and continue. And you can see how when I continue, GDB says, the process exited normally. That's because it returned a value of 0, okay? So this time we'll check and see whether it can spot problems, okay? So I'll run again, 1.23, and then just an E, but without a number after that. So as I said a little bit earlier, this is actually syntactically incorrect. It is not consistent with the regular expression. And we know this is going to return a code of 2. Okay, so we'll run this code, press the enter key. And it doesn't really matter what the structure has at this point, but it does have the right information all the way up to here because the exponent is not actually specified. But if I continue any further, you can see how the debugger identified the process exiting with a code 02, and see how this message is different from the message that we saw earlier, which is the program exited normally. So any exit code of non-zero is considered not, quote unquote, not normal, and it's reported by GDB. If GDB says it exited normally, it basically means it has a return code of 0. Okay? All right, so let's give it an actual number to work with, and we'll make it kind of tricky, okay? So 1.23 times 10 to the power of 2 is 123. Would have been exactly the same thing as just if I just gave it 1, 2, 3, right? Okay, so we'll run this and print PD. Yep, it's just 123 with nothing or 0 in the exponent of 10. If I continue any further, it would return it will say it's exited normally because the exit code is 0. It has no syntax error. Okay, try it one more time, okay? Let's try the negative thing. So this time we'll run it one more time, just one more, and we'll specify a sign here and run the program, print, PD. And this time sign has a non-negative value, which means the number itself is representing a negative value. Everything else seems to work fine. So I just spot checked the program to make sure that it works for the most part. This is by no means a proof that the program does work in all cases. It's really just a confirmation that, yeah, it seems to work. Okay. So are we good so far with this program? All right. So the first thing I need to do before I forget is to get back to Canvas. Okay, where is that? Okay. Oh. Yeah, well, I can always do it here. All right, so this is the Tuesday, Thursday class. Let me move to today's class. And what I'm going to do is I'm just including the source code into this module, into the physical state, gates, and numbers module. So I'm just adding a file. And here's a new file. Choose. I'm already on the right file. Add item. Okay. So you should be able to find it at the very bottom of the module. It's already in Canvas at this point. I do not expect you guys to write code like this, okay? Because this is about parsing, it's about syntax, stuff, which is not the core content of this class. But you should be able to understand it, okay? Because it only involves concepts that you have already learned in cisp310 and 360. All right. So, on to conversion. So once you have the base 10 representation of a floating point number, the next thing we need to do is to do the conversion from base 10 to base 2. So the value that we try to represent is v, and v is kind of expressed like this. The first part is the sign. The sign doesn't really change, right? I mean, whether it's base 2 or base 10, we're still representing a non-negative number or a negative value. And we use exactly the same representation, whether the sign is a 1 or 0. So if the sign is a 1, we use a -1 for this expression, ternary expression. If sign is not if it's a 1, we use a -1. If it's a 0, then we use a 1 as a multiplier. That's just controlling the sign itself. At this point, we have a base 10 number, which means we have a mantissa in base 10. Which basically that's the same thing as our the member called man10 in the structure. And then we have exp10, which is e subscript 10 in this notation, but they mean exactly the same thing. Okay, it's just that I can't use subscripts as a variable name in C and C++. I suppose I could use m_10 and e_10, but just notation. But the biggest question is, how do we convert it then? How do we convert it into some kind of mantissa in base 2 times 2 to the power of something? That becomes the biggest question. Because once we know how to do this, the floating point number is easy. Because the 52 bits is really just a fractional part of M2, okay? E, which is the biased exponent in base 2, is really just E2 plus 1023. So once we get to M2 and E2, the rest is really just moving bits around a little bit, okay? But the key is, how do we do this, okay? Because you can see in the desired form, there's no M10 anymore. There's no E10 anymore, okay? So how do we get rid of E10? That becomes the biggest question. Okay, so now we are moving on to this part. Getting rid of that decimal point is easy. We talked about that already. Okay, 1.23 is 123 times 10 to the power of -2. So that's how we got rid of the decimal point. Done. So now we need to look into, but how do we get rid of the exponent of 10? That becomes the tricky part. So instead of using M2 and M10 as two separate mantissas, we just say that we have a quote-unquote hybrid mantissa. It's nothing more than just a quantity. So it's a quantity times 2 to the power of something times 10 to the power of something. So initially, you can look at the base 10 version of a floating point number or scientific notation as having E2 being 0. Okay? It's not there. Okay? So what we want to do is to eventually make E10 0 and then E2 to be some actual value that works out. And during that process, we have the freedom to change M any way we want as long as it remains as an integer. Is that okay? So let me explain one more time what we're trying to do. We are trying to make E10 go to 0. The constraint is M has to be an unsigned integer. and e2 also has to be a signed integer. So those are our constraints. But we want to maintain v as closely as possible to the original v. Sometimes it's not possible, okay? But we want to make it as close as possible. So those are the objectives and constraints of what we are trying to do. Are we okay so far with the math of what we are trying to do? Okay. So if I want to turn E10 to 0, well, that means I have two directions to go. But before we go there, I'm going to talk about rounding, because there's no way to avoid rounding, because there are divisions involved, and every time you have divisions involved, unless the representation can actually store the precise result, you always end up with a rounding error. So we want to look into rounding a little bit and see how we can do rounding without floating point math. Why are we avoiding floating point math again? Well, there are two reasons. One is, what if this is the most basic library that you're writing and no floating point math function is already there? Well, okay, that's reason number one. The second reason is floating point calculation can be very costly in terms of processing time and also energy. So you want to avoid those if you can, okay? If you can do integer division instead of floating point division, integer division is so much less expensive. Okay, so we'll look at a scenario because we're always rounding. So let's take a look at the actual rounding definition first and see if I have that. Okay, well, I sort of have it. Okay, to take the round of something is, okay, so the round of x is really the floor function of x plus 0.5. Okay, so let me use a tablet to explain this part, because I think this one is a little bit harder to explain without using that. Now you know my password. Okay. And I did Monday, Wednesday one. Okay. All right, so what was I explaining? Right, rounding. Okay. So rounding is like this, okay? Wrong color. Back. There we go. So when you look at the rounding of a number x, you can implement it as x plus 0.5 and then take the floor function of that, okay? At least when x is non-negative. Well, let's check a few numbers. What is the rounded value of 1.1? Okay, not looking at the definition here. So which way would you round 1.1 to an integer? 1, okay. Huh? Down, rounded down by 1, yeah, to 1. About 1.9? 2, because 2 is the integer that's closer to 1.9 than the other way around, which is 1, okay? So we kind of understand what round is. The only value that's kind of like, well, we don't know about this one is, what about 1.5? So if you look at most definitions, the 1.5 rounds up to 2 and not rounding down to 1. Is that okay? So let's put those values into x and see if this works. Let's try 1.1 first. X is 1.1. 1.1 plus 0.5 is 1.6. And the floor of 1.6, which is basically the largest integer that is less than or equal to that number, is 1. Cool, that works. What about 1.5, the tricky one? 1.5 plus 0.5 is 2. The floor of 2 is 2. Okay, so it does round up correctly. So I think you're fairly convinced that this math does work out, okay? But it does involve the representation of 0.5. And if I only have integers, I cannot represent 0.5, right? So it sounds like we have a problem. Fortunately, the only time we need to do rounding is when we have a division of some kind, okay? So whatever we are rounding is always the result of a division of a numerator divided by a denominator. I just use N and D for its abbreviations, okay? So you substitute the entire n divided by d, or n over d, as x over here. So it becomes n over d, and then the whole thing plus 0.5, right? That's not too difficult. We know that. So if you multiply 0.5 with d, and then you use d as a common denominator for the entire thing, then you end up with n plus, and then 0.5 d, and then the whole thing divided by d. Is that okay? And you might argue, but we still have a 0.5 here. Well, what if d is an even number, like 2 or 10, that sort of thing? Well, exactly. Then 0.5d becomes 1 when d is 2, 0.5d becomes 5 when d is 10. So if you're rounding and you need a division by 10, then it's really just the same thing as whatever number you're trying to divide, plus 5 first, and then take the whole thing, and then take the whole and divide the whole thing by 10. Can we do that in C without using only integers? Sort of, right? What about that floor function thing? The floor function is there to get rid of the fractional part of the division. How do we do that in C? It's done automatically. When you do integer division, it's automatically taking the floor. In other words, we don't have to do a single thing about taking the floor, okay? We just have to pre-compute what is 0.5d, and fortunately 10 and 2 are both even numbers, and we just perform integer addition, integer division, and we're done. We can do rounding without using floating point numbers. Isn't that cool? I think it was pretty cool. Okay. So now, understanding this particular principle, now we look into a subcase of what if the exponent of 10 is currently less than 0. Well, if it's less than 0, we want it to become 0, which means which way do we want to change it? We want to add 1 to it, right? Well, what about jumping it all the way to 0 directly? Well, maybe that's a little bit too ambitious. But if we keep adding 1 to a negative exponent of 10, eventually it will get to 0, don't you think? Okay, so that approach does work. Okay, so that's what the first paragraph is saying. We need to increase E10 to 0 because it's negative to begin with, when at the same time decreasing E2. So those two kind of have to trade places, okay? So the general strategy is to divide the mantissa m by 10. That doesn't seem to make sense. Let me think about it. Yes, it does make sense. Okay, I'll tell you why it makes sense. Because when you divide the mantissa by 10, then you have to increase E10 by 1 to compensate for that division in order to maintain V. Right? Okay, so let me write out the math here on the tablet side. Okay, so we started off with some m times some 10 to the power of E10 times some 2 to the power of E2. Okay, so we want to do something like this. So we want to say, oh, well, we're going to divide m by 10. But in order to adjust for that, then we have to adjust E10 by increasing it by 1. Okay, nothing is being done to E2 at this point. Can everybody buy this argument? If I subtract 10 from the mantissa, in order to maintain the same V, which is the value represented, I have to add 1 to E10. Okay, and since E10 is a negative value, E10 plus 1 is now 1 step closer to 0 than before. Right? Okay. So that's why we have to divide m by 10. And that process, can have rounding issues. So what we do is we try to minimize the rounding issue, the rounding error. So how do we minimize the rounding error? So to understand how we minimize the rounding error, let's consider a few m's, okay? And you tell me, which one has more error. So let's look at 3, 36 divided by 10, and we do the rounding. Okay, so remember we are doing the rounding. So bad penmanship, ROUND. And what is that again? Yeah, okay, so, well, I'll spell out the entire thing. So 36 plus half of 10, the whole thing divided by 10, which is 36 plus 5 divided by 10. We take the floor of that, which is automatic in C. So we got a 41 divided by 10. We take the floor, which is a 4. Okay. Okay, no big deal. But how big is our error? In other words, comparing the rounded result of 36 divided by 10 versus the actual 36 divided by 10, what is the ratio of error? It's about 10%, okay? So I'll just call it about 10%. Okay, so we'll say about 10% of error. Is that okay? Okay. So we'll take a look at another example. Let's quadruple 36. So when you quadruple 36, what do you get? 36 times 4 is 144. So we say 144 divided by 10. And, okay, I'm pretty sure you guys don't need all the math here. Okay, so we'll just skip all the way to the result. It's going to be 14.4, but take the floor function of that. So it's basically 14, right? What about the error this time? It's smaller, but how much smaller are we talking about? So we are talking about 0.4 out of 14.4, right? I'll call that about, what, 20%? No, wait. 0.4 out of 14.4. What is the approximate value of that? Huh? 2.85? Let's call that 3%, okay? Oh, okay. So it seems like, we can, if we make the numerator bigger and bigger, since we're always dividing by 10, if the numerator gets bigger, then the error gets lower. Is that making any sense? But TAC, you can't do this because 36 is 36. 36 is not 144. I can do this because I have E2. I can play with E2, right? So if I want to bump my mantissa from 36 to 144, what do I need to do to adjust for that quadrupling of the mantissa? E2 now needs to be 2 smaller than before, right? Because I need to, somehow, somewhere, there has to be a division by 4. But I can do a division by 4 by decreasing the exponent in base 2 by 2. It's free for me to play with. I don't have to make E2 0. I need to make E10 0. E2 is completely free for me to use. Oh, if that is the case, why don't we bump 36 all the way to as large a number as possible in base 2 that can be represented? Because when that number is divided by 10, the error is going to be so small that it is really negligible. Is that making any sense? Okay. All right. So how big do you think we can make 36 as a base 64 as a 64-bit number? How do we figure out that math? Okay. So let me present the math here. So I want to say 36 times 2 to the power of some unknown x here. I want this to be less than or equal to 2 to the power of 64, the whole thing minus 1, as close as possible. How do I figure this out? I want x to be as large as possible so that this inequality still holds. How do I figure that out? Now remember, I cannot use log because log is a double function, okay? But I can use loops, okay? Because loops involving integers are fairly fast, and we can do that. So if I say you can use a loop to try to find out what x is, how are you going to write that loop? What is the condition that you to stay in the loop and say, nope, x is not quite big enough. Let's go for another round.
I would suggest can we start from 64 and count down because that may be where is it bigger than it, and if it's bigger, so
But remember, you cannot represent anything. Your unsigned 64-bit number can only represent values up to 2 to the power of 64 minus 1. So if the multiplication results in a product that is bigger than that, then you cannot compare anymore. So none of the calculation can end up with a number that is greater than 2 to the power of 64 minus 1. So that is the restriction. That's the one thing that is making it kind of tricky. Because, how do we do this? Because if you use, if you keep doubling, okay, a number, and you say, I'll keep doubling until it is greater than 2 to the power of 64 minus 1, that condition will never be satisfied. Because 2 to the power of 64 minus 1 is, in fact, the very largest value you can represent using a 64-bit unsigned number. Nothing as a 64-bit unsigned number can be greater than what is on the right-hand side already. And if you make the left-hand side keep doubling it, you're going to run out of digits. And C doesn't complain about it. It doesn't raise an exception. It doesn't care. So when you run out, it will just simply become a very small number again, and the loop will just be a forever loop. Yep.
take the one right below it. So 60 x, the greatest x can be is 63.
Say that one more time.
Could you just make x, the greatest x can ever be is 63? Could you just do that?
But it still involves a power function because you're still raising to the power of something, and the power function is a. Now you can use a shift operation to do the same thing, but when you multiply 2 to the power of 63 to 36, it's already exceeding the amount that you can represent using a 64-bit unsigned integer. So you still end up with the same problem. So how do we find out, yeah, we can't do another loop anymore, let's get out? Yep.
So I was thinking you could find the closest power of 2 that 36 is in.
But that involves log.
Well, find any remainder. Well, I mean, you take the remainder, but how do I describe this? Basically, what I'm thinking is because then once you find the closest it is with a with a remainder, then you can subtract it from the 64 and then subtract one more from it.
Well, when you say remainder, that implies a division.
Well, more like I'm thinking more subtraction.
Subtracting. So what is the minuend and what is the subtrahend?
So you're taking 36 minus the closest power of 2 you have as a representation of it, and subtract it from 36.
Okay. So you're trying to compute, basically without computing, you're trying to find out what is the log 2 of 36. And then that will basically, you just subtract that amount from 64, and then you can determine what x is. Okay, so I see the approach. Well, that approach has merit, okay? It definitely works for the most part. The tricky part is, what if this is not 36 and it's 32? It is exactly a power of 2. So it can be off by 1. Now you can probably adjust that logic and make it work. But the other way to do this part is to see whether the number that you might want to multiply is already 1/2 of the largest possible number already. Because if it is already at least 2 to the power of 63, you cannot double it anymore. That's it. You see what I mean? Okay, so let's see if this. I'll write this logic here, and you guys see whether it works or not. Okay, so we'll say it's a for loop. Okay, and we initialize x to 0. X is really just a counter to see how many times we can get through the loop here. And then this 36 is in a variable called I'll call it m, okay? So 36 is stored in a variable called m, which is our mantissa. And what we're going to do is to say if m is less than, okay, 2 to the power of 63, then we can go through another iteration. The post operation is incrementing x by 1 and also multiplying m by 2. So m plus multiply equals 2, and that's my for loop. What do you think about this for loop here? Do you think it will do what I want to do here, to find the maximum x so that my mantissa becomes the largest possible value in 64-bit unsigned? That is, yeah, that's basically the bottom line. What do you think? I think that'll work. Is there a fast way to do this? I mean, comparison is pretty easy to do. But how do we know a number is less than 2 to the power 63? What is the one thing that is common to every single binary number that is greater than or equal to 2 to the power of 63? Okay, so we are dealing with 64-bit numbers. So I have to add that as an extra constraint. So with that extra constraint, every single unsigned number that is at least 2 to the power of 63 has bit 63 being a 1. The most significant bit has to be a 1. So this logic can now be specified a little bit differently. So I can now say about the same thing, x equals to 0, m is less, nope, not less than anymore. This time we use a bitwise AND operation. So bitwise AND with a number where only bit 63 is a 1. So how do we specify that? And this will confirm when it is a 1, which is opposite to what I want to do. The rest is the same, except the multiplication of m can also be done using a bit shift operation. So I'm shifting it to the left by 1 position. How about that? These two loops really mean exactly the same thing. One involves only bitwise operations, whereas the other one has arithmetic operations, because less than involves a subtraction, multiplication, and so on. The other one only involves left shift and also left shift. Yep.
So for doing the two less than symbols, that just means you're shifting it to the next bit from 63.
So you mean the less than operator? That's known as the left shift operator. So it takes 1, which is the least significant bit being a 1 and everything else being zeros, right? And it's quote unquote shifting that 1 63 times to the left. And every time you do a shift, it is introducing a 0 on the right hand side. So that means, basically I end up with a number where bit 63 is a 1 and everything else being a 0. And that turns out to be 2 to the power of 63. And every number, yeah, go ahead.
Sorry, m and that.
So you mean this one here? So this one here is the same thing as multiplying m by 2. It is the same kind of construct. It's called a compound assignment operator, where it is an assignment operator, but it is also performing an arithmetic operation. So in the case of m star asterisk equals 2, it's the same thing as m equals to m asterisk 2, which is multiplication by 2. In the case of m less than equal 1, it is the same thing as m equals to m less than 1, which is shifting the entire mantissa to the left by 1 bit. But those two are basically the same thing. They're equivalent operations. So that would do it. That would do the trick. Okay, so this way, m ends up to be as large as it possibly can, and then I'll go ahead and do the division. Is that okay? But there's one little problem here. There's always that little problem, right? The little problem has to do with when we do rounding, we have to do m plus 5 and then the whole thing divided by 10. So if this m does end up to be a number that's greater than or equal to 2 to the power of 63 minus 4, then we have a problem because adding 5 to it will make the numerator not representable anymore in 64 bits. Is that making any sense? So that means, when I perform this operation, the range compare is not exactly quite as simple as that. So I can't really use the bitwise operation because of that. In fact, I have to change this number to make room for that plus 5. Is that making any sense? Because the number cannot be has to be less than or equal to 2 to the power of 63 to the power of 64 minus 1 and then minus 4. Minus 1 and then minus 1 and then minus 5. So it's minus 6 altogether. So that's why, I have to kind of make sure that that happens. So this number, now fortunately 6 is also divisible by 2. Right? So that means, this number has to be 2 to the power of 63 minus 3. Okay, so let's look at the boundary conditions. A boundary condition is when a value is right at the value that you're comparing to. So it's not a bunch below, it's not a bunch above. It is exactly where you specify the boundary. So let's say what happens when m equals to 2 to the power of 63 minus 3 itself. Okay? Well, if it equals to, the condition is false, and we get out of the loop. But the question is that the right thing to do? What if we go through the loop one more time? In other words, what if we double this? When m is already 2 to the power of 63 minus 3, and we double it, what do we get? We get 2 to the power of 64 minus 6, right? So we can still perform this operation. So we can still perform one more iteration. So that's why we have to change this to less than or equal to catch that one single instance, so that we squeeze the last bit of error reduction out of this logic. So after this whole thing, okay, the final version is for x equals to 0, m is less than or equal to 2 to the power of 63, but remember to subtract 3 from it. Okay. And then the rest is the same. Add x, m. This time we can just shift by 1. That part is not a problem. So this becomes the last and the correct version of maximizing m, but still leave enough room for the rounding trick. Is that okay? And then we do a division by 10, right? So getting back to the notes. So then we perform a division by 10, and then we add 1 to the exponent of 10 because it was negative to begin with. So now it's one step closer. And then what do? Go back to the beginning. Is E10 still less than 0? If so, maximize the mantissa again. Do another division by 10. Increase E10 by 1, and then go back again. So you keep doing this until E10 becomes 0. So what you will end up with is a mantissa that is really big, okay, and a E2 that is really small. Because every time you double M, you have to remember to subtract 1 from E2. So in the logic that we had earlier, you basically have to subtract you have to subtract from E2 the X amount in the loop. So is the logic okay? What happens when E10 is less than 0? How do we bump it up to 0? Yes? No? Yes? Okay. What about it's the flip side? What if E10 is positive to begin with? Then what should we do? We want E10 to be 0. So if it's positive to begin with, what do? Decrement it, right? Okay. But how can we decrement E10 without changing the value represented? Well, in order to decrement E10, we have to multiply the mantissa by 10. Does that make any sense? Every time you multiply the mantissa by 10, you can decrease the exponent of 10 by 1. Okay? So we can keep doing that until E10 is 0. But in the process of doing this, okay, in the process of multiplying the mantissa by 10 again and again and again, you might end up with a mantissa that cannot be represented by a 64-bit number anymore. And then what do? What do you think? M becomes so large that it is not representable using a 64-bit number anymore. So what are you going to do? You divide M by 2, and then what do? If you subtract the mantissa by 2, what do you have to do to compensate for that? Increase E2 by 1. Exactly. So it's kind of the opposite of what we did earlier. So when you look at the strategy here, the first thing we do is, as long as M, which is the mantissa, is not less than the largest integer value divided by 10, then we can keep doing this. In other words, we just have to make sure that the next multiplication does not bump it over. Okay? And doing this means we are making M small enough to have room for another multiplication. Is that okay? So we are trying to make enough room to have room for another multiplication, and then we have the multiplication, and then we adjust E10, and then we go back and try to make room again.
That means you'll have to divide it by 2
That means we have to divide it by 2.
more than once because
Yep.
you're multiplying by 10.
Yep. Yep. So the number of times you have to divide it by 2 varies between 3 and 4. It's because 10 is between 8 and 16. 8 is 2 to the power 3, and 16 is 2 to the power 4. So most of the time you have to do it like 4 times. No, most of the time you have to do it 3 times, and then occasionally you have to do it 4 times. So is that okay? So by the end of section 5.2, okay, we would end up with a number that is a value, I should say. We'll end up with a value expressed as a mantissa times a non-zero times 2 to the power of some potentially non-zero value times 10 to the power of 0. So we would have gotten rid of exp10 or changed that to 0. So after that, it's just a matter of shifting things around, moving bits around to become the double precision number format. Is that working or not? Now, I would love to demonstrate it using a spreadsheet, except it doesn't work in a spreadsheet. The reason why this kind of math doesn't work in a spreadsheet is because a spreadsheet doesn't actually use a 64-bit number to represent values. So once I get beyond a certain number, a certain value, it becomes a floating point number, and the values are not exact anymore. And this math cannot be illustrated using a spreadsheet. Now, if I reduce the size of the floating point number, I can probably do it. So if you look into IEEE floating point numbers, there are several formats. And let's see, let's go. And basically they're only different in terms of the precision. So let's see. Okay, this is the smaller one. A single precision floating point number has, okay, let me show you the picture because you will recognize the picture. No, doesn't have a picture. There we go. Remember this picture? This is just a little bit smaller. So we still have a single bit to indicate the sign of the overall value. We have E, which is this time an 8-bit number that is unsigned. And the bias, if I remember correctly, is 127. And the fractional mantissa, and this time it only has 23 bits. But reduced to this particular format, I can actually use a spreadsheet to illustrate what I mean when we go through the calculations. Let's see, we got 10 minutes. So are we okay so far with the math that we just talked about? If EXP10 is negative to begin with, we want to increase it. But the only way to increase EXP10 is to divide the mantissa by 10. But division by 10 can potentially introduce a lot of errors. So we want to make the numerator as large as possible before the division. Okay? But every time we double the mantissa, we have to remember to subtract 1 from E2, which is the exponent of 2. And that's how we do the conversion when EXP10 is negative. When EXP10 is positive, it's quote unquote easier because all what we need to do is to keep multiplying the mantissa by 10 because every time we multiply the mantissa by 10, we subtract 1 from EXP10. Now, if you can do all that without exceeding the range of a 64-bit number, it's all good, easy peasy. But what if you get to a certain point and go like, if I multiply this number by 10 one more time, it's going to be exceeding the largest value that we can represent in a 64-bit unsigned number, then you have to play with base 2. The way we play with base 2 is we subtract 2 from the mantissa, or we keep subtracting 2 from the mantissa until there's room to multiply the mantissa by 10 again. But every time you divide the mantissa by 2, you have to increase E2 or EXP2 by 1. So that's how we adjust, and we gradually turn EXP10 to 0 by adjusting the mantissa and also the exponent of 2. So are there any questions about the general scheme of how to get this done? Well, I got a question. What if we don't do the rounding? So instead of doing the rounding trick, we just say the floor of the division. What's going to happen? Okay, let me ask you this question. Okay. So instead of using round, some large number divided by 10, okay? What if we just say, x divided by 10 and then take the floor, because integer division is automatically taking the floor for unsigned numbers. So yeah, go ahead.
Introduce much more error.
It's going to introduce errors, yes, but errors is going to be there anyway. Even rounding doesn't get rid of errors. But what rounding does is to make sure your errors are not biased. In other words, when you're rounding, sometimes the rounded value is a little bit more than what it should be. Other times it's a little bit lower than what it should be. And the chances is like 50-50, okay? So half the time rounding is going to make it a little bit bigger, and half of the time it's going to make it a little bit smaller. So in the end, unless you have some really, really odd value where rounding keeps erring in one direction, for the most part it's going to be pretty close to what we want it to be. Okay, after repeatedly doing rounding, it will still be pretty close to what we want to be. If you do not do rounding and instead you do a floor function, then we have a problem because now we have what we call a bias in the calculation. Every time you have an error, it's making it smaller. Every time you have an error, it's making it smaller. So all that error is going to be cumulative, and what you end up with is the converted value is going to be significantly smaller than what it should be, as opposed to, well, it's close, it's as close as it can be, okay? As opposed to, whoa, it's way smaller than what it should be. So that's why the rounding trick is extremely important, because without rounding, the conversion process will give you a representation that is way smaller than what it should be. Okay? So are there any questions about all this stuff? Yep.
I have a small question.
Yeah.
The way you notate the floor function,
Mm-hmm.
little L's.
Yeah.
What about when you have only just one L next to something? I know you usually put.
I'm forgetting something if you don't see only one. Okay, so one more question because we got 3 more minutes. All this logic, all the code that we're going to write to do the conversion, why does it matter? I mean, if you look at all the Intel processors, the i5, even the i3 processor, the least expensive of all the processors, it already has a floating point unit. In other words, we don't really need to do all this stuff. There are C libraries to read a string and convert it into the double precision floating point number format. So what is this useful for? Well, has anyone heard of the Arduino? Okay, what is an Arduino? It's a tiny little single board computer, okay? So what about it? How does it compare to an i3 processor?
It is a very small processor.
It has a tiny little 8-bit processor. Do you think that tiny little 8-bit processor that can run continuously from a AA battery for almost a month, okay? Do you think it has a floating point unit to do floating point number calculations? No. Do you think it comes with only 8 kilobytes of program space? Do you think it comes with a conversion subroutine to convert the string into the double precision number format? It's expensive, okay? It does has a library to do it, but it takes up a lot of space, okay? So that is why, if you understand this logic, you can basically roll your own logic to do the conversion. If you know what the input format is going to be, then you can do your own conversion. I used to work for a embedded system company. Basically we use the same kind of, not the same kind, but they're 8-bit processors lacking, floating point calculations. Okay, and even hardware multiplication is kind of like a late, addition as a feature. So we have to squeeze, every last ounce of performance out of that processor. So understanding the underlying implementation of something like this was actually very important. And that's partially why, we, in this class, we not only talk about the representation itself, but we also talk about the conversion process. Because, you might end up, with a job where your boss says, we can't use an i3 processor here. Why? Because it's a Fitbit. Why do you think i3 would not be a very good fit on a Fitbit? No pun intended. Huh? Power consumption, exactly. So my Fitbit can last 5 days without a single recharge. So if my Fitbit is i5 based, even using the latest 14 nanometer technology, how big of a battery do you think I would need to last 5 days when it's actively tracking my motion, heart rate, and all kinds of stuff? Probably heavier than what I want to carry with me, right? But this, using a smaller 8-bit processor that has limited processing power, yeah, it's not the fastest, but it gets the job done, and they can sell it for $100. If I use an i5 processor, do you think they can sell the watch itself for $100? Probably not. So there are a lot of applications where your boss will say, yeah, I know the i5 processor can do this, but we are not using an i5. We're going to use an AVR or some lesser processor because the power ratio is better. That's something that we'll talk about again, in the class, is about cisc versus risc. But today we are running out of time, so we're going to transition to the lab now so that the next class can come in. And I'll see you guys over at the lab. If you get there before me, well, in the odd chance, the passcode is Mantisa. But I'll be there as soon as I